Devin. Yeah, so as he mentioned, I'm an MEng student here at the DCI, being mentored by Neha and Taj. Today, I'll be talking about my research, which is looking into mitigating a type of mining-related attack called an undercutting attack. And I'll talk about how I studied and modeled mining behavior and the transaction fee environment to do so. So as a quick overview about what I'll be covering in the presentation today, I'll start off with some background, such as what are the motivation and goals behind my research. I'll then talk about the mining strategies that we modeled, including the aforementioned undercutting attacks and how they work. And I'll also give a brief overview of the simulator that we use to model these strategies and to measure their relative effectiveness. Then I'll cover the current progress that I've made in my research, specifically the mining aspects that we modeled, such as the block size limit and the fee gradient. And I'll talk briefly about the preliminary results that we've had based on from our simulator regarding how these affect the undercutting dynamic. And finally, I'll wrap it up with a brief conversation about the next steps and where we go from here. So to start off with a bit of a background, undercutting attacks were a mining-related attack first proposed in a 2016 paper called On the Instability of Bitcoin Without the Block Reward. And the intuition behind this is essentially that block rewards, which is a certain reward that is given to miners for building a block, is rapidly dwindling and eventually will disappear. And what this means is that a miner's revenue will be solely based on the transaction fees, on the transactions and the fees that they can actually include in their block. And with no block reward, this increases the variance in the rewards a miner can get between blocks, because some may have more transaction fees in them, some may have less, just based on the transaction fee environment. And without a block reward it's harder to offset that difference. And this increased variance in mining rewards invites this type of undercutting attack, which is essentially where miners will intentionally fork the blockchain to steal the transaction fees from a previous block and make a new block on a new fork. Now, the security implication of this attack is kind of frightening, because undercutting attacks promote repeated forking of the blockchain, and this can lead to lots of stale and orphan blocks being left over, which increases the risk for other attacks, such as 51% attacks, and in extreme cases can lead to the breakdown of the consensus algorithm if the forking happens so often. So what exactly is the goal of my research? Well, the original paper made many assumptions that don't exactly accurately reflect today's mining environment or what we hypothesize the mining environment to be in the future. And so what we aim to do is to investigate how changing these original assumptions to be more realistic would affect the efficacy of these undercutting attacks, and to propose ways to encourage the conditions that render undercutting attacks ineffective, in the hopes of neutralizing this threat in the long run. So now I'll talk a bit about the mining strategies that different miners can take, including undercutting attacks, as well as the simulator that we built to model them and compare them. So the first type of mining strategy is just a default honest miner. If everyone was default, everything would be great. The default miner would always extend the oldest or the first seen chain and create a block with all the remaining transactions in the mempool. So for example, in this graphic we have here, the default miner would take the oldest chain, which is chain 1, and build a block from the 10 transactions remaining in the mempool. Now, the second type of miner is interesting. It's called a petty honest miner. Now, the petty honest miner itself is not a threat to the blockchain because it doesn't fork the blockchain. But what it does instead is it picks the chain with the most transactions available, not necessarily the oldest chain. And it also clears out the mempool and builds a block from those available transactions. So in this example, the petty honest miner, rather than building on chain 1, will instead build on chain 2 and create a block from these 55 that are available. And so these petty honest miners create an opening for the undercutting miner, which is the crux of the problem. So these undercutting miners are parameterized by a coefficient f. We'll denote this as fork f throughout the presentation. And basically what an undercutting miner does is it takes a chain and creates a new fork. It then looks at all of the transactions that are available, including those that were already previously mined in that previous block. And it will take 1 over f of those transactions and create a new block in this new fork and leave the rest to incentivize the petty honest miner. So let's take a more specific example to see how this really works. So let's say we have an undercutting miner with a coefficient of 2. So what this means is it'll create a new fork. It'll look at how many transactions we have total. So there's 100 from the previous block, 10 in the mempool, that's 110 total. 1 over f is half, so we take half of those 110, and which means we take 55 in this new fork, create a new block, and leave the other 55 as incentive for the petty honest miners to join their fork. And indeed, we see this is the case. As mentioned before, the petty honest miner will choose chain 2. The undercutting miner also gets more profit than they would have originally if they were default honest. Default honest only get 10, undercutting miner get 55. But at the cost of adding this new fork, and this previous block of 100 is essentially moot. The reason why we sort of call this stealing is because they're sort of stealing these 55 from the previous 100 when they're creating this new fork. So now that we understand the different strategies, it's easy to reason about in a one-round scenario. If we have one specific environment of a mempool, a blockchain, and these miners, it's easy to reason about, but it's harder to model these strategies and understand their effectiveness over the long run when we're looking at more than just one mining round. And so this is where the simulator that we built comes in. These simulators help us model the strategies, help us model the real mining environment, allow us to control the incoming transactions, and allows us to reason about the effectiveness in a concrete way over a long period of time. So specifically, the way the simulator works is for each game, at the beginning of the game, each miner is assigned a strategy, petty honest, default, or some flavor of undercutting miner. Then for each mining round, we simulate transactions entering the current mempool, and we can control this and code it as we need. And then each miner uses the code from their strategy to interpret the state of the blockchain and the mempool, and uses that information to pick whether to undercut if they're an undercutting miner, and to choose which transactions they want to actually include in their block. Then after multiple of these mining rounds, at the end of the game, each miner's profit is calculated based on which of their blocks actually made it into the final chain and which of their transaction fees they ended up mining. And the higher the profit a miner has at the end of the game, the larger the strategy weight that is assigned to them becomes. And this essentially indicates that more miners adopt the strategy. So the strategy weight can be thought of as what percentage of miners are adopting the strategy. And this continues and repeats multiple times over multiple games as miners use a no-regret learning algorithm to gradually learn which strategies are actually more profitable over an extended period of time. Eventually, towards the end, it'll reach an equilibrium, which signifies that miners agree in general on how effective and profitable each of these strategies are. And so when we say undercutting attacks are effective, the way this translates to the simulator is we consider undercutting attacks to be effective if the weight of the undercutting strategy at equilibrium is greater than the strategy weight of the other strategies. In other words, all the miners agreed that the undercutting strategy would yield a higher profit. So now that you understand in general what the attacks are and how we're measuring it, I'll dive deeper into what the current progress we've made in our research is, starting off with adding the idea of a block size limit to our mining simulator. So the original paper assumed that a single miner could clear out the entire mempool, put all the available transactions in the block with no limit on the amount that they could that they could use to build a block. Now, in a way, this does occur occasionally when there's a low volume of transactions, because the total number of transactions in the mempool is so small that it would never actually fill a full block. So the block size, as enforced by the blockchain, is irrelevant for the purposes of the paper. And the implications for this with regards to how this affects undercutting is if there's no limit and a miner can clear out the entire mempool and leave none for the next miner, then the next miners will definitely have an incentive to undercut, right? So if we take a one-round example where we have 200 transactions available in the mempool, the first miner could take all 200, leave 0 for the next miner. So the next miner will have to undercut if they want any transactions. And they will, take those 200, steal 100, leave 100, and they'll have more revenue. And this is sort of the reasoning that the original paper used to show that undercutting attacks are effective. However, this is not always the case. Especially recently, there have been a higher volume of transactions that are available and waiting to be confirmed. And it's infeasible to take all of these transactions and put it into a block because we're limited by the size of the block. And this leads to a backlog of transactions that are waiting to be confirmed, but can't yet because of the block size constraints. And so essentially what we did is we rewrote the mining strategies in the simulator to reflect this idea that a miner can only take a number of transactions up to the block size limit. And this is a graph of the real mempool transactions. Ignore the colors for now, we'll touch on that later. But as you can see, the peaks are a lot higher than previously, and it's infeasible for us to take all of these transactions and put it in a mempool. Now, the implications for undercutting when we do have a block size limit is that because a single miner can't clear out all of the mempool and there is this long backlog of available transactions, the next miner can still try and mine from that backlog, and there's more than enough left for them to mine from that backlog. And this de-incentivizes undercutting because we can get a very similar profit by continuing and mining from the existing transactions on the honest chain. And there's no need to steal from a limited transactions from a previous block. So looking at a similar example as the last slide, if instead we're limited to only taking 100 transactions per block, then the first miner can only take 100 when they're building the block, leaving 100 in the mempool, which is more than enough for the second miner to make their block. So even if they wanted to try and undercut, even if they wanted to try and undercut, they'll still get the same profit anyway, so they would end up just continuing and they have no incentive to undercut. And indeed, we do see this dynamic when we implemented it in our simulator. Specifically, we saw that as long as the block size limit is at most 60% of the transactions that come in, the amount of transactions that come in every round, the backlog that ends up being built is sufficient enough that there is always enough available in the current mempool for the next miner, so they won't need to undercut. And so let's take a look at the graphs here that show this. So this graph on the left-hand side is an example graph from the original paper where there are no block size limits. And this shows that undercutting attacks are effective because, as we can see, this undercutting miner that takes half of the available transactions, so in our lingo, fork 2, has a high strategy weight of around 0.6, which signifies 60% of the miners end up actually undercutting. Whereas when we restrict the block size to any percentage less than 60% of the incoming transactions that come in every round, we can see that all of these strategy weights are all the same, meaning that that means that all the miners agreed that all the strategies are essentially equally effective, which means undercutting doesn't give you a leg up, so undercutting attacks are essentially rendered ineffective. So the next mining aspect that we wanted to add is the concept of a fee gradient. And this is where the colors from the previous graphs come in. So the original paper assumed that all the transactions had the same fee, the default fee of 1 Satoshi per byte. And this would hold in low volume times, like what is assumed in the paper, where there is no backlog, so no real limit, no real block size limit. And under these conditions, it's always possible for a transaction to make it into a block because there's just so few in general. So users have no incentive to set any higher fees beyond the default because they don't need to incentivize miners to take their transactions. They will take it regardless. But under the new model where there is a backlog and not all transactions can make it into the first block, some users may be incentivized to pay higher fee rates in order to try and get their transactions confirmed and in a block quicker. And this is indicated by the color with red signifying very high fee transactions and blue down here signifying what was before like 1 Satoshi per byte basic low fees. But this presence of different fees means that two transactions that have the same size can have drastically different revenues. And this changes the undercutting dynamic because especially when size is a limiting factor, these high fee transactions become more lucrative because you can get a higher revenue for the same slot, so to speak, in the block. So let's take a look at an example where we have a limited block size and we also have a high fee transaction. So for example, let's assume we have a large mempool full of regular low fee transactions, and this previous block has one high fee transaction of 2. Now, if we were to continue and we're limited to only taking 3 transactions in our block, then what we would do is we would basically take 3 of these transactions and we would make a new block. However, if we have the option to undercut, now we can take this high fee transaction of 2. Now this high fee transaction of 2 is more efficient. It only takes the same slot. It only takes 1 slot in that block, but it yields a higher profit, which means the undercutting miner actually has a profit of 4. So under this case, undercutting wins. And this seems to suggest that if there are high fees, that undercutting might be reintroduced where it wasn't before. But there's an interesting added dynamic here is that if high fees are common, for example, if they come in consistently every single round, then undercutting actually isn't effective. So let's see a similar example, but this time in this new mining round, we have new transactions that come in, including another high fee transaction of 2. Then in this case, the continuing miner can take that high fee transaction and 2 of the others and also get a profit of 4. Undercutting miner will behave the same way. They'll take the high fee transaction from the previous block. And since in this case, there is a high fee transaction available in the mempool, as well as in the previous block, both of their profits are the same. So miners will continue and continuing wins. And this interesting example seems to suggest that it's not the mere presence of high fees in the mining environment that might encourage undercutting, which seemed to be suggested by the previous example. Rather, it's when the high fee transactions are sparse enough that we can't get it from the current mempool and we have to get it from the previous block. So now let's take a look at the preliminary results that the simulator showed us. And indeed, it does seem to match the intuition that we've shown on the previous slides. So the first case is that high fees come in every round, which is very similar to the example that we just saw. And in this case, both the current mempool and the previous block have that high fee transaction. There's equal incentive to continue versus undercut. So undercutting strategies are not effective, as we can see in figure 1, where all of these strategy weights are exactly equal. Now, the second case is high fees come in very rarely. So rather than coming in every round, let's say they're super sparse, they only come in every 10 rounds. Now, this is a really interesting dynamic in that, yes, these undercutting miners will undercut to get those high fees because it will match the most closely to the first example I showed. But because these high fees are so rare, the extra profit that we get from these fee transactions is minimal and not statistically significant enough to actually convince the other miners that undercutting is sufficiently more profitable over the long run. And this is shown in figure 2 here, where in general, it looks still quite similar to figure 1, where all of the strategy weights are still very close to each other. And so even though in this case, the high fees are sparse enough to encourage undercutting, they're too sparse to actually make enough of a difference in the long run to make undercutting attacks actually effective. And then the third case is probably the most interesting case, in which high fees come in every other round. And this is sort of the Goldilocks zone, where it's just sparse enough that the current mem pool won't have a high fee transaction because it comes in every other round, but the previous block will, so they will always undercut to get that high fee transaction. And because it comes in every other round or 50% of the time, this undercutting action occurs frequently enough that it's statistically significant, and the other miners are convinced that undercutting attacks are actually profitable. And this is shown in figure 3. So this gray line here is fork 2, which is basically, again, where a undercutting miner forks, takes half of it, and leaves half for the other miners. And as we can see, it's up to around 55%-ish of the miners agree that taking this flavor of undercutting is more effective than the other strategies. So under this specific environment, undercutting attacks, the threat of undercutting attacks is reintroduced. So that's in general the current progress that we've made, but there are many other aspects that we'd like to continue investigating. The first of which is that there are many different types of transaction fee distributions. Right now, we're looking at a sort of simplistic one, right, where there are majority of a low fee default and a few high fee transactions, but there can be multiple tiers of different transaction fees beyond just high fee, low fee. There's a gradient, right, as by virtue of the name, and we'd like to model these different types of gradients and see how these affect undercutting. And we'd also like to continue looking into how this frequency of the high fee transactions specifically affect when undercutting stops working. So, for example, between high fees coming in every other round versus high fees coming in at 10 rounds, at what point does it go from undercutting attacks working to undercutting attacks not working? So aiming for more specificity on this. The second part we'd like to look at is trying to obtain real Bitcoin transaction data to better understand what conditions, what dynamics, what mining environments are actually realistic in the past, and therefore what do we hypothesize mining environments to look like in the future. And this will help us to understand the general feasibility of these environments and strategies that we're modeling in the simulator are. And finally, we'd like to continue investigating ways to mitigate the effects of these attacks. For example, how can we discourage the set of conditions that we found that allow undercutting attacks to be profitable? Maybe by limiting block size to a certain percentage or a certain number, or somehow encouraging a certain high fee or fee gradient transaction dynamic that is the most conducive to keeping undercutting attacks from being effective. So that's the end of my presentation. Thank you all for listening, and definitely let me know if any of you guys have questions.
Yeah,